Out of the three types of subatomic particles that are present in an atom, the only one that cannot be different if you're looking at the same type of atom or atoms representing the same element is the number of protons. The number of neutrons can be different. You can have two atoms of the same element and you can have a different number of neutrons in those two atoms. The number of protons will still be the same because you're looking at atoms of the same element. So whenever we have atoms representing the same element but with a different number of neutrons, what we're referring to is as isotopes. Every element that is listed on the periodic table will have isotopes. There are mainly two types of isotopes. Isotopes that are stable and in which the ratio between the protons and the neutrons is not too far from what is listed on the periodic table. And then we also have isotopes that are unstable, and those type of isotopes are classified as radioactive. And we have a whole topic for chemistry that is dedicated at nuclear chemistry, in which all of those nuclear processes and involving radioactivity are explained. So just looking at the examples that I have listed here, I'm still using the element carbon, atomic number 6 with a mass rounded to 12. Now I have on the table here listed two isotopes of carbon. We have a specific way of representing the symbol of an isotope. It's similar to what we get to see on the periodic table, but not exactly the same. I'm going to use the letter X for a generic symbol for any element that is listed on the periodic table. And I'm going to use letter A here and letter Z here. So to represent the symbol of an isotope, we use this notation here, the symbol of the element. On the top left side, we have the atomic mass of that isotope. And then on the bottom left side, we have the atomic number. Okay? The atomic number is going to be the same if we're looking at two atoms of the same element, but with different number of neutrons, or in other words, isotopes. That's one way of representing the symbol of an isotope. The other one is something like what I have on the table right here. X representing the symbol for any element on the periodic table, dash, and that will be followed by the mass, okay? Which I'm using letter A to represent. So if I'm representing, let's say, the isotope of carbon here, carbon 12, using the notation on the left, that one will look like this, 12, and here atomic number 6. If I'm representing carbon 13, that one will look like this. Instead of 12, the mass will be 13. Now, we know at this point that the mass is given by the addition of the total number of protons plus the number of neutrons. We're defining the mass of each proton as 1 AMU. Every neutron has a mass equal to 1 AMU. So adding those masses together will give you the mass in atomic mass units. So if the mass depends on the number of protons and number of neutrons, but the number of protons is the same because we're looking at atoms of the same element, right? If the number of neutrons is different in isotopes, that means that the mass for the isotopes are going to be different. That's why in my two isotopes that I have listed on the table, I have carbon 12, carbon 13. That number is representing the mass. You have a different mass for those two isotopes because the number of neutrons is different. The number of protons is given by the atomic number, and we're looking at carbon. So atomic number for carbon is 6. Regardless of the mass of the isotope that we're looking at, the atomic number is 6 because the isotopes are isotopes of the atom of carbon. Okay? So it contains 6 protons because that's what gives carbon its identity. Now, if we want to calculate the number of neutrons, that's the symbol for neutrons, that will be the mass minus the protons, which is the atomic number. So number of neutrons for the first isotope listed on the table, the mass is 12 minus 6, the number of neutrons is 6. For the second isotope listed here on the table, the mass is 13, the number of protons is 6, so the number of neutrons is going to be 7. We have the same number of protons because these are isotopes of carbon. We have 6 as the atomic number for carbon, regardless of the mass of the isotope. And then the number of neutrons is different. We have 6 neutrons when the mass is 12, and then we have 7 neutrons when the mass is 13. So two isotopes of carbon, they have the same number of protons, but different number of neutrons. When we look at the periodic table, we get to see the elements, and they have a mass listed for each specific element. So the example that I've been using is carbon, and probably you already remember this. The number is something close to 12, right? But we do have some decimal places. Now, when we're using those masses to find out the number of neutrons that you have in each specific atom, we're rounding that number to a whole number. Like, I didn't calculate my number of neutrons using 12.011 as the mass of carbon. I was using that number as a whole number. Now, we do have decimal places because that mass is actually calculated using the masses for all isotopes that we have for a specific type of atom. Like, for example, I have listed here 3 isotopes for neon, mass of 20, mass of 21, mass of 22. We know that isotopes are atoms of the same element that contains different number of neutrons. So for neon 20, right, atomic number for neon is 10. So we're going to have 10 neutrons because the mass is 20, mass minus the number of protons, which is the atomic number. And for neon is 10, we're going to have 10 neutrons for that isotope. Then for neon 21, we're going to have 11 neutrons and then 12 neutrons right here. Now, isotopes exist in nature, but they don't exist in an equivalent amount. Like, we don't say that we have 33% of one isotope for neon, 33% for the other, and 33% for the other. We actually have a percent of abundance. We can find tables with those numbers. So these are not numbers that you need to memorize or anything like that. So, but you can see like a clear difference, right, in the magnitude of those numbers. Like, I have neon with a mass of 20 or neon containing 10 neutrons with an abundance that is close to 90%. So that percentage is, just to put it in perspective, what it means is that if you take 100 atoms of neon, right, at random, and you check, okay, how many neutrons do I have in these 100 atoms of neon? Out of the 100, 90 of them, 90 of those atoms are going to contain 10 neutrons, right? That's 90 of 100, that's 90%. Okay? So the majority of the atoms in that sample of 100 atoms are neon with a mass of 20. So again, we have neon 22, that's something close to 9%. right? So 9 atoms are going to have 12 neutrons in that sample. So I'm just rounding the percentages here a little bit just to give you an idea of what the percentage is representing. Now, we know that the majority of the atoms are of neon, right? I'm looking specifically at neon. Majority of the atoms are going to contain 10 neutrons for neon. So if we calculate the masses, right, using an average that takes into consideration also how many atoms contain a specific number of neutrons, then that amount is actually going to affect the average that we're calculating. So for example, I have an equation here that I'm not going to use in any example, but just to give you an idea of what the percent of abundance means. That's just converting your percentage to a decimal number. Okay? So I have 90.48 divided by 100, and then that's the mass for that specific isotope. So I'm looking at my percentage here that corresponds to neon 20. The mass is 20. So that will be times 20. This part in your equation means the sum of. So we're adding all of them together. I have 3 isotopes, so I need to add that factor that I have here plus the same for the second isotope plus the same for the third one. Now the biggest contribution to the average mass is coming from this first term here because that will give you the biggest number. Okay? So we can actually predict which isotope is the one that exists in the highest abundance just by looking at the periodic table, right? The mass that you have in the periodic table comes from the addition of all of those masses for each isotope. When you look at the periodic table, if you have it available, you can do it just now. You can find neon on the periodic table, and the molar mass that is listed, the mass that is listed for neon on the periodic table, it's actually a number very close to 20. And the reason is that even though we have isotopes of neon with 11 neutrons and with 12 neutrons, the majority of those atoms contain 10 neutrons, which is going to give you a mass equal to 20. So the mass that is listed on the periodic table is actually very close to the mass that we have for that isotope that exists in nature in a higher abundance. So I have here another example of isotopes for a specific element on the periodic table. In this case, I'm looking at hydrogen. So hydrogen, the isotopes for hydrogen are special because they actually have a name, contrary of the isotopes for other elements. Okay, they don't have an actual name. So we have protium, deuterium, and tritium as the 3 isotopes for hydrogen. Now I'm using this example because I don't have a percentage of abundance for the isotopes of hydrogen listed, but we can actually predict which one out of the 3 isotopes that I have listed here, which one is the one that we can find in nature more frequently. The atomic number for hydrogen is 1, is the first element listed on the periodic table. It's on the left side of the periodic table, right? But even though it's on the left side of the periodic table, it's still classified as a non-metal. It does share properties with the metals that we have listed right there in group 1, but hydrogen is actually a non-metal. So atomic number 1, and we have like the representation for the symbol of the isotopes here. Remember, number on the top part is representing the mass. The number on the bottom part here is just your atomic number, which is giving you the number of protons. So the isotope of hydrogen named protium it has a mass equal to 1, it has an atomic number equal to 1, and the atomic number for all three isotopes is the same because we're looking at isotopes of hydrogen. So the atomic number is giving you the number of protons, which means that this number of protons is the same for all three isotopes. Now the number of neutrons comes from the mass minus the number of protons. So when we find out like the number of neutrons, right, if we're looking at the first isotope listed here for hydrogen, which is protium, the mass is 1, the atomic number is 1. So when we calculate the number of neutrons, we're going to get 0 neutrons. So at some point when I was going over the subatomic particles, right, I'm talking about the 3 types of subatomic particles, and I mentioned like in general, right, all of the atoms are going to contain these 3 types, right, not just 3 subatomic particles, but 3 different types of subatomic particles, the protons, the electrons, and the neutrons. And that in general comes from this reason here. So we're saying that all atoms are going to contain protons, electrons, or neutrons, but then here we are looking at this hydrogen with atomic number equal to 1 and a mass also equal to 1, which means that you do have a proton, but there are no neutrons in this specific isotope of hydrogen. Okay? So this is why I was saying in general. Okay? So we're expecting to have all of these 3 types of subatomic particles, but in this specific example, we have no neutrons. Okay? For the second isotope listed here for hydrogen, the deuterium, we have a mass equal to 2. Atomic number is still 1 because we're looking at hydrogen. So for the deuterium, we do have 1 neutron. And then for tritium, with a mass of 3, mass minus the atomic number, which is 1, that will be 3 minus 1, and you get 2 neutrons for that one. Now, my goal with this example here is not to go over again how to get the number of neutrons and protons for the isotopes. The real reason is just to go over the abundance of the isotopes in nature. If we look at the periodic table, right, I'm not giving you the abundances for the isotopes like I did with the neon. If we look at the periodic table, right, we can find the mass of hydrogen. It's something very close to 1.008 usually in the periodic table that I use. So that number is very close to 1. When we look at the masses for the 3 isotopes of hydrogen, we have protium with a mass of 1, deuterium with a mass of 2, and then tritium with a mass of 3. The mass that you have on the periodic table is 1, and that's a mass that is obtained when we add the masses of the isotopes together, right? Using that equation, that is your fraction times the mass of each isotope. So it makes sense that if the mass listed on the periodic table for hydrogen is very close to 1, it's because the isotope of hydrogen that exists in nature in a greater abundance is going to be protium, which has a mass equal to 1. Okay? We do have the isotope with 1 neutron, the isotope for hydrogen with 2 neutrons, but the majority of the atoms of hydrogen that exist or that we can find in nature are going to have 1 proton and 0 neutrons to have a mass equal to 1. And that's why the mass that you have listed on the periodic table for hydrogen is very close to 1. It's because the isotope of hydrogen that exists in nature in a greater abundance is going to be protium. So I'm going to do just one of the 3 examples that we have listed here, and you can do the other 2. So finding protons, neutrons, and electrons, you actually need to look at the periodic table. Okay? So try to have the periodic table with you for this one here and for the next one that I'm going to be doing, so you can actually look at the periodic table and have an idea that of where to find the numbers, so you know for sure that you don't need to memorize those numbers. Okay? I'm looking at the numbers from the periodic table. Okay? So let's do the second example. Remember, when you're looking at the symbols for the isotopes, what you have here is the mass. What you have here is the atomic number. For my other possible notation or representation for the isotope, like this one here, the atomic number is not given, but that's perfectly fine because you have the symbol of the element and you can use that to find the element on the periodic table. So it's oxygen, you find oxygen on the periodic table and you can get the atomic number of oxygen from the periodic table. Another thing, if for example at some point, right, you don't remember which number is the mass, which one is the atomic number, just remember that the mass depends on the number of protons and the neutrons, and the number of protons is the atomic number. So the mass number in general is a greater number than the atomic number. Okay? So it makes sense that the 22 is representing the mass for sodium because you have the protons as part of that 22 plus also the neutrons, right? For the atomic number, you only have the number of protons. So looking at the mass and the atomic number for that isotope of sodium that is listed there, number of protons is given by the atomic number, so that will be 11. And then we have that the number of neutrons is the mass minus the number of protons or the atomic number. Since the mass is 22 and the atomic number is 11, 22 minus 11 is going to give you 11 neutrons. And then the number of electrons. Okay? When you have neutral atoms as they are represented on the periodic table, the atoms for the elements are neutral, and that means that you have the same number of protons and electrons. If each proton is representing a positive 1 charge and each electron is representing a negative 1 charge, right? When you have the same number, total number of positive and the same total number of negative charges, you're going to get 0. So if you have 11 protons, which is 11 positive charges for sodium, to get sodium as a neutral atom, you need to have also 11 electrons. So when you have neutral atoms, the number of protons and the number of electrons is exactly the same. And one more, the last one. Mass number, letter A, atomic number, letter Z, and then we're looking at an isotope of argon with 18 neutrons. So we have two possible ways of representing the symbol of an isotope, and I'm going to write down both. We know that we're trying to get argon, so you can check the periodic table to find out the symbol for argon, and that's Ar. And now you're given the number of neutrons, you need the atomic number and the mass number. The atomic number for argon you can get also from the periodic table. Argon is element number 18. So when you're writing down the symbol for an isotope, on the left side, on the bottom part, you have that atomic number. And then on the top part, you're going to have the mass number. For the specific isotope that you're looking at in this problem, the mass number is going to be 36 because your mass is coming from the addition of your protons plus the neutrons. The protons are given by the atomic number, which is 18, and the problem is telling you that that isotope for argon contains 18 neutrons. So when you add your 18 protons plus the 18 neutrons, you're going to get a mass that is equal to 36. 18 protons plus the 18 neutrons. So that's one way of representing the symbol of that isotope. The other way is just to write it like this. the symbol of your element followed by the mass of the isotope. You don't need to include the atomic number, but this problem specifically is asking for the atomic number, which means that the preferred notation that you have to use to answer this specific question will be on the one on the left. If the problem is not asking you to find out or to write down the atomic number, then you can use the notation that I have on the right, because that is just telling you that you have the isotope of argon with a mass of 36, which is that isotope of argon that contains the 18 neutrons that you have listed on the problem.